Okay, it's 1 o'clock. We can get started. Hi, I'm Gina Cannarozzi from the Chemistry, Biology, Pharmacy Information Center at ETH Zurich. And today I'm going to be talking about AlphaFold and the family of programs that they have developed. So what is AlphaFold? It's a solution to the protein folding problem. That is predicting protein structure from protein sequence. So it's relatively easy to get the protein sequence, which can be represented as above, as a molecule or as a sequence of amino acids. And this folds into a three-dimensional structure, which looks something like the thing on the bottom. And to go from here to here is not that simple. But AlphaFold seems to have solved this problem. And why do we need protein structures, or why do we need protein structure predictions? Well, you can determine them experimentally, and these are the gold standard of protein structure. There's three ways to do that, either X-ray crystallography, NMR, or cryo-EM microscopy. But these are time consuming and can take from weeks, months, years to get one single structure. And so if we can predict the protein structures in high quality, this has a lot of value. Okay, as a reflection of how hard it is to get the experimental structures, you can look in the protein data bank, the PDB, which is the repository for experimental structures. And in March 2025, that was a few days ago, there's not quite 233,000 experimental structures. The first structure of a protein was from 1958. So in the 70 years since the first structure, there's relatively few structures here. The structures are stored in the PDB as XYZ coordinates of each atom, and this is also the output of the AlphaFold program. So AlphaFold is a product of DeepMind. DeepMind is a company that specialized in artificial intelligence. They started in 2010, United Kingdom, and then they were acquired in 2014 by Alphabet, which is Google's parent company, and now it's called Google DeepMind. So they started working on this problem around 2016, and I think by 2021, they've pretty much solved the protein folding problem. And now they're moving in different directions. So what is AlphaFold 2? This is the successful program that got them a lot of publicity. It's basically a very complicated deep learning neural network. And so with a neural network, you have two phases. You train the neural network, and then you can predict with it. In the training phase, they used 180,000 experimental protein structures from the PDB. So the input is the sequence and the structure, which you can get from the PDB. From the sequence, you can find related sequences and build a multiple sequence alignment like this. So the main information that AlphaFold is working with is they're looking for covariance. And covariance is, if you look at these two colored columns in the multiple sequence alignment, you can see every time one changes here from R to K, it changes here from D to E. So these two are varying together. And what that implies is that they are close in three-dimensional space. So what AlphaFold does is it looks at every single pair. It comes up with a covariance matrix. So each element in the matrix has a numerical value of the strength of the covariation between those two pairs. And using this pair representation and the multiple sequence alignment, that's what they use to make the predictions. So once you train the neural network in AlphaFold 2, the output is around 21 million parameters, and these parameters characterize the model. So basically, in doing this training, AlphaFold is learning the relationship between the multiple sequence alignment, the covariance matrix, and protein structure. And once you have your model, which is defined by the 21 million parameters, you can make predictions with it. So typically what happens is you have a sequence, you don't have the structure, and you can create a multiple sequence alignment, or AlphaFold does that for you. Put it in the model, and the output is a structure, and the structure has confidence estimates. So here the blue is highly confident predictions and the orange are not. You have something that looks like this. So the core of the protein is predicted with high confidence, and then these ends are kind of floppy. These have lower confidence. So the timeline of the development of AlphaFold is so fast that you can't even do it by year. You have to put in the month. So it started around 2018. To preface this, in the protein structure prediction community, there's a contest called CASP, and that's where the community looks to see who has the best methods. And if you look at the timeline here, you can see that from 2006 to 2016, there was almost no progression. AlphaFold came in 2018. This was AlphaFold 1. They did considerably better than what had been done for the previous decade. And after these 2 years of refining the model in 2020, they did extraordinarily well and were getting predicted structures with scores almost as high as experimentally determined structures. So this is when they started getting a lot of publicity in 2021. They were the science breakthrough of the year. And at this time, DeepMind released the source code for AlphaFold 2. So you have the source code available. In the next prediction contest, which was 2 years later, they didn't participate. They stopped developing AlphaFold 2, but everybody else was using it. And this is a word cloud created from the CASP 15 presentations. And you can see the AlphaFold played a huge role, even though they weren't actively participating. At that time also, DeepMind collaborated with the European Bioinformatics Institute, the EBI, to make AlphaFold DB. And they basically applied AlphaFold to every existing protein structure that met the criteria for using the program on it. And so now, by 2022, they have predicted 230 million protein structures, and compare that to the 230,000 experimental structures that we have. So if your protein structure is in a database, it more than likely already has a prediction for it. But if you have a proprietary genome or proprietary data, you can run it locally and get the structure for it. So at the time of when AlphaFold 2 was doing so well, people started trying to predict protein-protein complexes. So you could join two proteins with a long linker, and AlphaFold could actually find the interaction sites between these two different proteins. And so at that time, they made AlphaFold Multimer, which does a better job than just adding a linker, and it's made to find, for example, you have a bunch of proteins coming together in a complex here, and it can determine the structure and how these different proteins fit together. And then in 2024, the Nobel Prize in Chemistry was awarded to DeepMind's Demis Hassabis and John Jumper for the protein structure prediction, together with David Baker, who worked on protein design. So that's kind of the pinnacle of how far you can go with a software project. Okay, since that time, they've released AlphaFold 3, and it seems like the protein structure community is moving past just doing protein structures, and now they're predicting interactions. And that's what AlphaFold 3 does. AlphaFold 3 predicts joint structures of complexes, including proteins, protein, nucleic acid, include small molecules, include ions, and it can also predict proteins that have post-translational modifications, which was not the case. So before this time, all of these separate interactions, like protein-protein was one program, protein-nucleic acid was another one, and AlphaFold seems to outperform a lot of these specialized programs with their one deep learning neural network. AlphaFold 3, however, is not fully open source like AlphaFold 2, and so If you can get a non-commercial license or an academic license, but you can't use it the same way you use AlphaFold 2. So for example, this is from the AlphaFold 3 paper. Here they have a protein bound to DNA, and they've predicted the structure of both. Here's the coronavirus spike protein, which is heavily glycosylated, and you can see it also has some ligands there, and they've predicted the structure there. So this is from the AlphaFold 3 paper. They are in blue, so you can see that they're outperforming a lot of methods. I'm still waiting on the output of the CASP-16, which was in December 2024, to get the big picture of who's at the top of the list now. So if you want to run AlphaFold at ETH Zurich, it's on the Euler cluster. All ETH students, faculty, staff can get an account on the Euler cluster, and ETH Scientific Services has very clear instructions on how to run AlphaFold 2 and AlphaFold 3. If you want to run AlphaFold 3, you have to go to Google to download the model parameters, and you have to assign an agreement directly with Google. So since we're academic users, this shouldn't be a problem. But if you are a commercial user, then the rules are different. If you're not at ETH, they also have a server you can use, but the tokens are limited. So if you go to the AlphaFold website, it looks like something like this. They have now just links to the AlphaFold DB database, AlphaFold 3, and this server. So the conclusions of this are, at this point, it seems like the protein folding problem is pretty much solved. AlphaFold 2 doesn't create experimental structure. That's still the gold standard, but for a lot of applications, they do something that's good enough. And AlphaFold 3 is now producing high accuracy modeling of complexes with a lot of different kinds of interaction partners. The difference is AlphaFold 3 is not fully open, so you have to make an agreement with Google to get access to it, but academic users can do that. So thank you for your attention. The coffee lecture card is right there if you'd like to take one if you're in the room. And otherwise, you can download the digital coffee lecture card. And I'd like to draw your attention to tomorrow. Tomorrow's coffee lecture will be Yoshi Dolence, who will present browsing, which is a convenient way to keep track of all of your literature. So thanks. Are there any questions? Or